Alright, here we go with the very last lecture of Unit 1. And if you want to keep up with in the textbook, this material is covered in section 2.7 of the textbook. And that section is titled Inequalities. So we're going to open up with linear inequalities. So that means there's no squaring, cubing, no variables in denominators, no absolute values, no radicals, no funny business. Just good old-fashioned linear expressions thrown in with an inequality. Now, an inequality just means it has a less than or equal to, greater than or equal to connector in it. So, solving linear inequalities is actually going to be exactly the same as solving linear equations, except there's two key differences. And the biggest difference is when multiplying or dividing both sides by a negative, you must flip the inequality sign. So if you ever multiply or divide both sides by a negative, you have to flip that inequality sign in order to maintain the truth value of the statement. All right. And then the second big difference is that your solution set is typically going to be a range of values when you solve an inequality. So to represent a range of values, we typically use interval notation. And let me go ahead and explain that interval notation right now. So x is less than 4. So when we say this, here's 4. If we take all numbers below 4, that'll be everything on the number line to the left. So we shade in every single number below 4, and then we typically use an open dot when making a number line to represent an open set, so to speak. And the reason we use an open dot is we can pick numbers that are infinitely close to 4, but we can't include 4 itself. If we include 4, we would have a false statement because 4 is not less than 4. But I can pick 3.9. 3.9 is less than 4. 3.99 is less than 4. 3.999999999 is less than 4. And as you can see, we can get infinitely close to 4, but can't actually include the 4. So this is a number graph of the solution set. Here's how we write the solution set in interval notation. So we simply just read from left to right. So whenever we have the graph, writing the intervals pretty straightforward. The shading starts at negative infinity and stops at 4. Now, you'll notice I use parentheses here. So let's compare that to this statement, x is greater than or equal to 4. So in this example, I still have 4, and x is greater than, so that'd be all the numbers above 4, so that's everything to the right of 4, shading in. And here we'd have a closed dot, because a closed dot means we can't include 4. So 4 would satisfy the statement. 4 is indeed greater than or equal to 4. Now if we were to write this in interval notation, reading from left to right, we would have bracket 4 to infinity. So the bracket means the value is included. Parentheses means that value is not included. So make a note right now. If you need to pause, go ahead and do so. Make a note. You use parentheses when the value is not included. You use brackets when the value is included. So basically, anytime you have a strict inequality, you'll use parentheses. Anytime you have an or equal to inequality, you're going to have brackets somewhere. Let's go ahead and finish up these examples. So if I look at this example, x is greater than 4. So notice we cannot include 4, so it's an open circle, and we're selecting all values above 4. So if we read from left to right, the solution set starts at 4, stops at positive infinity. Notice everything there is parentheses. And if we look at this inequality, it's 4 again. Notice the or equal to, so we'll shade it in, and this is all values equal to 4 or below it, so that's to the left. So this shading starts at negative infinity, so we always read from left to right. Starts at negative infinity, stops at 4. 4 gets a bracket because the value is included. Alright, so that's interval notation out of the way. Let's go ahead and look at some actual examples, starting with example 1. So you would solve this just like a regular old equation. So we'll go ahead and distribute. So that gets us 4x plus 16 minus 2 is greater than x plus 1. So let's combine like terms. 4x plus 14 is greater than x plus 1. So I'm going to go ahead and subtract x from both sides and subtract 14 from both sides. Now with subtraction, you don't have to flip the sign. So 4x minus x is 3x. 14's cancel, so 3x is greater than negative 13. And then all that's left is to divide by 3. Notice I do not have to flip the inequality sign because we divided by a positive. If we divide by negative, we have to flip. And oops, I made a mistake. The directions say write the solution set in interval notation. So if you're struggling with interval notation, take 5 seconds, draw a quick graph. So there's negative 13 thirds. It's not included in the solution set. We're picking everything above it, so that's to the right. So in interval notation, the solution set is parentheses negative 13 thirds to infinity. So what this says is you can pick any number in this interval and it will satisfy the original statement. All right, suppose we pick 0, in which case we would get negative 2 is, let me see here, is greater than 1. Was there a mistake somewhere? One second here. Oh, no, it works. Sorry, I made it arithmetic error. If I plug in 0, that'd be 16 minus 2, which is 14. 14 is indeed greater than 1. So yeah, it works. Sorry. Made a mental error there. So yeah, it works. So let's go ahead and look at the next example. So basically when you're solving a linear inequality, you just do what you would normally do. You work towards getting x by itself. Now notice here, this is different. I just divided both sides by negative. So anytime you divided by both sides by negative or multiply by negative, you're going to have to flip the inequality. So what I'm going to have to do is flip that inequality symbol around. So notice that I flipped it around and that gives me negative 2. So if I were to make a number graph, my solution is all numbers equal to negative 2 or below. So the solution set is negative infinity to negative 2 with a bracket. Now if you forget to flip, your interval will be completely wrong. You'd be saying pick any number above negative 2 and it'll work. Well, if we pick a number bigger than negative 2, say 0, it won't work. Say if we plug 0 into the original statement, we would get 5 is greater than 13. That's false. We have to pick a number below negative 2. Suppose we pick, say, negative 5. Well, if I plug in negative 5, then you would get 5 plus 20 is 25. 25 is greater than 13, and that does work. So you have to pick numbers below negative 2 in order to make this statement a true statement. So let's step it up to compound inequalities. So a compound inequality is multiple inequalities combined into a single inequality. There are several ways we can do this. This is where we kind of get into unions and intersections. We won't be getting that complicated in this class. We're going to be focusing entirely on AND statements. So if we look at this type of compound inequality, it's just basically saying, hey, x is in between a and b, in this case greater than a, but less than or equal to b. So the strategies remain the same here. You just want to get x by itself. The only thing that's different is we now have 3 expressions to work with. So what you do to one expression, you do to all expressions. So in this first example, we just subtract 1 from everything, and we get our solution set. And if you want, you can make a quick little number graph. Oops, sorry, there's a mistake there. That's a strict inequality right there. So got negative 4, positive 4, negative 4 gets a closed circle, Positive 4 gets an open circle, and we're going to go ahead and shade everything in between. So there's our solution set. Bracket -4 to parentheses +4. Basically pick anything in between -4 and 4, and you will satisfy the statement. Now let's look at example number 2, and if we go to get the x by itself, we'll start by subtracting 1 from all expressions. So that's -6 is less than -2x, which is less than or equal to 10. Now notice here, to get the x by itself, I divided everything by a negative, so we still have to flip. So we just divided everything by a negative, so we're going to have to flip the inequality signs. So here I would get 3, flip the sign, x, flip the sign, -5. So this is where a graph can be very useful to help get our bearings straight, because -5 is actually to the left of 3 and the number line. The flip has messed us up a little bit, so this is where the number line can be really useful. -5 is getting a closed dot, 3 is an open dot, x is in between. So our solution set is anything in between -5 and 3, including -5. Alright, that is compound inequalities. That brings us to the last topic for Unit 1, absolute value inequalities. And we talked about absolute value talked about absolute values in the last section. Absolute value measures distance from 0. So let's go ahead and think our way through these problems. So when we look at example 1, absolute value of x is less than 5, we're trying to think, hey, what numbers are less than 5 units away from 0? Well, here's 0. So I can go 5 to the left at -5, 5 to the right. We want to think, okay, what numbers are less than 5 units away from 0? Well, that's going to be everything that's in between, less than 5 units away. So that's any number in between -5 and 5. There's our solution set. Now, if I flip it around, what numbers are more than 5 units away from 0? Well, then the sky's the limit. I can go way out to the left into the negatives, or I can go way out to the right to the positives. So here we would actually have 2 intervals. So we can pick anything below -5 or equal to it. So that would be -infinity to -5. And note the or equal to, so that's a bracket. Or, so that's where we draw the union symbol, it can go from 5 to infinity. So you can see the numbers are the same, but the conclusions are very different. So this theorem summarizes our observations. If the absolute value is less than a positive value, then you're going to have a compound inequality. If absolute value is greater than a positive value, then you're going to have 2 separate intervals. Now, we got to keep in mind absolute value is always non-negative, so we could have a special case. That's why in the theorem we're assuming that c is a positive constant. If we look at this example down here, absolute value of x is less than -5. Let's say, okay, what numbers are less than -5 units away from 0? Well, you can't have a distance below -5 because every distance value is positive. There's no such thing as a positive number below -5, so this is actually no solution. Now let's look at number 2. We want to go ahead and isolate first. So let's go ahead and isolate this. We can do this divided by -3. Now it's still an inequality, so remember when you divide by a negative you have to flip that sign. So we had to do a flip there because we divided by a negative. Now this is saying distance is greater than -4. Well, absolute value greater than -4. Well, absolute value of anything is going to be positive or 0. Well, every positive number is greater than -4. So this is actually all real numbers. You can actually input any number you want. This statement will always be a true statement. Alright, so you can plug in 0, you can plug in 0.0001, you can plug in a million, plug in any number your heart desires. This statement in number 2 will always be true. So just be careful. If it's a special case problem, that doesn't automatically mean no solution. It just means it's either no solution or anything's a solution. So let's go ahead and wrap up with 3 more examples. So what we're going to do is we're going to go ahead and apply that theorem on the last page. So distance is less than 3 units. So we have -3, +3. So we got to ask ourselves, is our expression in between or outside? Well, distance is less than 3 units away. That means it's in between. Right? If some unknown value is less than 3 units from 0, well then it's going to be bounded. So then we get a nice compound inequality that's pretty quick to solve. So x is in between -5 and 1. So there's our solution set, all parentheses. Now compare that to example 4. Distance is greater than 3. So we got a 3 to the left of 0, 3 to the right of 0. We got to ask ourselves, is our expression in between or outside? Well, distance is more than 3 units away from 0. So that's going to be out past the -3 or out past the +3. And so here we have 2 completely separate inequalities. So when we go to solve them, we get -5 over here, we get 1 out here. And if we were to graph this, here's our -5, here's our +1. They are included in the solution set because it's an or equal to inequality. And our solution set is beyond, it's on the outsides. It's below -5 or above +1. So when I go to write the solution set, the first interval starts at -infinity, stops at -5 with a bracket. And then the next interval starts at 1 with a bracket and ends at +infinity. So here, for 2 separate shaded regions, we'll have 2 separate intervals. Now let's look at our last example. We want to go ahead and isolate it first. So we do that by dividing both sides by -2. Now when we do that, we have to flip the sign. So don't forget to flip it. So distance is greater than 4 units from 0. Well, I got -4 and +4. I can go 4 units to the left or 4 units to the right. We got to figure out, okay, is our expression bounded between these 2 numbers or beyond these numbers? Well, distance is greater than 4, so it's going to be beyond these numbers. That's going to be beyond +4 and beyond -4. And then we'll go ahead and solve these. So we'll just solve these real quick. So here you get -7/2. Over here you would get 1/2. So if we wanted to put these on a number line, so we have -7/2 on the left, 1/2 on the right. They are both included in the solution set because they're or equal to, and they are beyond these values. So if we write our solution set, that's -infinity to -7/2 with a bracket, union 1/2 to infinity. And there we have it. And thus we have our solution set for example 5. Pick any number below -7/2 or any number above 1/2 and you will end up with a true statement in this case. Alright, well that's a wrap on Unit 1. I've covered everything that's on that quiz, and I've also covered everything on the test review, so feel free to begin working on those, and have a wonderful day.